to approve us basically since 29. The mission extensions is a very critical point, and you should never underestimate and take it for granted that your mission is extended. It forces basically to evaluate the science case and basically to make a new science case and ideally pointing things which could not be done before. As it's not convincing we have some sources forgotten for 20 years. The point is to say there is science which we can do now, which we could never address before. No, this. This is frozen. Oh, what? Okay. Clearly, we are based on publications. This is all publications found by the body search mentioning XMM Newton, and then I classify them all. And basically, the first 5 classifications we use basically to sell our results. And it is here the first, the blue using data, then the red is using the catalog or the pipeline products. This between is in catalogs or describing the missions. And very important is transformative science, new things. I think this is fascinating. We could see separate the corona, the spin of the black hole, antimass only within XMM Newton measurements. And here's this quasi-periodic oscillations. This is an original source detected in the XMM Newton's laws. And here basically what we get on paper in Science and Nature using XMM Newton data. And you see here, because we had it before, we had very few in the beginning, and there were some doubtful results at the beginning, and I am sure Nature and Science were basically stopping further publications for some time. But then we could recover here. Clearly, the paper needs data, and this is the data usage. It is from 2014. We want to redo this exercise, and first plots look very similar. And we have a very, very high rate of papers versus papers on each observation, and not only the big catalogs which are on top. And if you compare this to typical optical telescope, our big one, the ESO, they run here by 30%, to 33. Most paper data which they are producing are produced to enrich the archive, whereas we produce most to write papers. This is an oversubscription, and clearly oversubscription papers are the mean argument for extensions. Here we had a very high in the beginning. This was really too high. It dropped, then it was decreasing, and then it's stable. The oversubscription is less fluctuating. We had this big exception here with 9.6 here, but then it is more or less stable over the years. And we have this multi-year heritage programs. I come later here back to some. If you look on the long term of the mission, but better if I look now backwards, it is a big question, what is the discovery space? And XMM is your built as a spectrometer. And even if the CCDs are, this was the best possibility technology at this time to get the iron line. The gratings have much, much less effective area. There was a choice with XMM to go for effective area, and then the PN and MOS camera were the best what you could do. And the quality of spectra is given by the number of photons. It's a counting of photons, and we have the Poisson statistic. And then the question of the spectra is not the number of the photons, is the signal to noise. And this goes in with the time to the square. And if you have now, say, an observation with 10 kiloseconds, 5 kiloseconds is a minimum. And you want to get 4 times as much signal to noise. Say you have a line just detected, you want to see if the line is width of the line, then factor 4 is 40 kiloseconds. The next question is to get the asymmetry. You need a factor of 2 more in signal to noise, 160 kiloseconds. And a panel has between 400 and 800 kiloseconds for about 50 proposals. There you've seen in 3 or 4 steps, you run basically out that the panel would give you the time. It is quite similar for surveys. The signal to noise of a source population is proportional to the area, and then it's again with t quadrat. The other point is how much sources we have. How are the sources distributed in the sky? If I have a certain object class, how much can I do? If I find an object in A, how much I can look at in object B? These are the 56 optical brightest stars. This is here. Then basically a factor 2, then a factor 4 to see the next, and then it increases. In AGNs, the brightest from the Pichinocci, very simple. You have normally 1, 2 bright sources, and you have then a factor 5 less flux. And if you go here with a high flux, you have no chance to do this with a second source. And if you take this together, the statistic and this source population, then I have written 7, but I would better write 5 to 7 years. A mission has explored its discovery space. Then if all would be frozen, basically, it would be very hard to do new convincing things. And you can also see from the other side, if you look to these accelerators and so on, all this mission you plan typically of a lifetime of 5, 7 years, maybe 10, but not more. And if you want now, say the other way, if you have 7 years, if you now say you want to have a factor of 4 more statistics, you would need 28 years. And this is basically such a natural point. And 7 years is 2 PhDs. This is typically our turnaround time. What to do if you want? Yes. I looked into the paper from IOE. It's exactly the same criteria as I used for XMM, and we'll see, compare them later. The IOE was International UV Explorer, and it was basically the first facility to allow spectra on the UV. And you see here, you have this 5 years, 5 to 7 years to increase, and then this curve goes down. To the whole, I come later. What to do? New instrumentation, VLT with Gravitas, I think this is fantastic, but it's quite limited on space generations. HST got new instruments. I also proposed this for other satellites, which is seen as a joke in ESA, and we cannot do it. We have some 40% potential signal to noise from the cross calibration from the MOS to the PN. At the moment, we still have difference, but we hope that we can fix this, but it will not really change a lot. What optical facilities do? To go completely to research, high student numbers, shortage of institute-owned facilities in Europe. It is problematic for such a mission where you need an extension. You have to make the case in science to get this operational costs in. Change of science goals, this you see also by optical facilities. So you take a 2-meter or a 3-meter telescope, you change the camera and use it for a large survey in a, say, when 8 are coming. We studied this with XMM. Could we go to all sky survey mode? But XMM is extremely inefficient. Also, we would have about in the soft range half the efficiency with ROSAT. To do this ROSAT all sky survey, we need 2 or 3 times the time. A problem is also the background and so on, depending on our orbit. What is the point is to extend the discovery space beside now these options. And I think this was done with IOE. The IOE here, and here you see this peak again. And this comes not now with IOE alone, it comes with HST, is launched. They had problems at the beginning, but there was a lot of finding out for HST people or the IOE, the UV people. But then also with ROSAT, there were a lot of joint observations, and this allowed basically to stop this trend here and go back to this. Okay, expanding now the discovery space. So the first thing is the large programs, and basically these 3 steps to get the signal to noise higher. We allow here, say, 2 to 3 steps more. We have the large programs, which are more than 300 kiloseconds. Typically now, 45% of A and B priority time, this is a time which is guaranteed, goes to large programs. We have the long observation with variability studies as a mass and spin of black hole, but also this deep spectra of a weak object, the WIMPs, was 1.5 megaseconds, was in this, and then clearly variosample. And to make it even larger possible, we introduced these multi-year heritage programs with 2 megaseconds, offered over 3 years, performed over every 3 years performed. Here we have extragalactic surveys, the galactic center regions, then a large sample of Planck clusters, high redshift quasars, and now the last one, the Euclid field. And this is a distribution. We had one as a program with 300 and more kiloseconds in AO1, enormous problem in the OTAC as it was not foreseen. We put sensor regulation in place, and you see here, so after 5 it starts and the community uses it. The problem was this very large program. We had this very large programs. This was not really working, and now we had this multi-year heritage program, and I think this is now working very fine. The point is, such a multi-year heritage program or such a very large program have a completely different way of argumentation compared to the normal programs. And if you do this in a normal OTAC evaluation, this does not work out. The people don't make this step. The one is principally clear prediction what you want to measure and the time, whereas this multi-year heritage problem more such a strategic coverage of discovery spaces. And here is the same image basically in time, the different kind, but this is now all programs over 300 kilograms. Second program, joint programs. This we have from radio to TeV and AO, JWST since last AO, VLTI, HST, Swift, Chandra, NuSTAR, Integral, Hess, and Magic. I think nobody else in the whole Europe offers you such a possibility to get a really broad SAD. These programs have very, very different success rates. NRO is almost never used. With this, we were simply too late. I tried to get something in radio in Europe, it was a nightmare, rejected by them at the end. Then I got it from the Americans. I got 8% of their time without problems, but Chandra was there earlier. And if you have lost such an opportunity, it's over. NuSTAR, we got it full. This was fantastic. HST, okay. The most, something is only here successful if you can access the science. The point is, Planck, even it was no program with the Diashadovich effect, you measured the same as in X-rays. Enormous amount of follow-up. HST, the absorbing winds, outflows, and binaries compared, and NuSTAR most. Hess and Magic, we are very important to identify them. And here this is the distribution of them accepted here, basically, and this starts from 2010 and goes then up to 2015. This is basically the second change here after things. And here's the same plot in the time. And the last one is targets of opportunity, not foreseen in planning and developments, 4 weeks of scheduling in advance. Then we introduced only triggered observations as TOO were forbidden, that you in the minimum could ask for a source and say you want a certain state. And the director of science agreed basically for unanticipated TOO, answering a question during a press conference in the context of the launch of the satellite. With this public statement, we were allowed to make it. We changed here the rules to get it really smoothly through and to be able to react with a lot of time. And it's, again, important to have this in place in time before the others. And the triggers were Swift and here Rosetta. Now, and especially this Zwicky. The Zwicky is now this machine for it. Now you see the distribution, it was always, but it goes from 2015 to 20 up, and especially also in the time. And this is mainly driven by the Zwicky facility. There is an enormous amount of detection of tidal disruption events, and especially now to find atypical ones. Basically, the follow-up is mostly driven by atypical, but also all AGNs are carefully checked in China, especially if there is any behavior which is different. I have 1 minute left. Yes, the publications. Now you have this IUE, and this is for XMM. And you see we have this 5-year increase, and then basically we could keep it stable up and to go and ask for extensions. I have no but this is too late, but I was aware of it, what will come. This should be published now, is an AstroPH. If you were interested basically on the gender and success rate and devolution of XMM Newton proposals. Maybe. This is our ratio from male to female. It is 1.1. And HST after introducing the double anonymous has 1.09. The XMM Newton process gives basically is a result which the double anonymous, which other missions and facility reached only after introducing the double anonymous. And in my few graphs before, I try to explain how we will get rid of these biases. I think I have to stop here.
Thank you very much, Norbert. Oh, yes, I'm sorry. Okay. The question I have is about these joint programs with other missions. And I was wondering, I know that now CRIS doesn't foresee any XMM joint observation. I was wondering whether you already know or if for the next XMM AEO there will be joint CRIS proposal.
This is too early to make any comment.
Okay.
Okay, for a quick question. Yes.
We have joint observations a lot, but not a joint program.
Right. No. Yes. I mean,
yeah.
Still Axel Schwuppe, not Didier Barré. Can you comment on the success and the oversubscription of the multi-year heritage programs? How competitive are those? And how successful are those in terms of publications?
The oversubscription, the first was very high compared to the normal one. This one was low, but it was in the pandemic. I think such things are affected from the pandemic if people cannot meet. And the last one was basically exactly in line what the others have, other factors 1 to 6. The point is we have just the C targets. And this multi-year heritage, you don't, or the large programs, you can normally not give seed time. Therefore, you have really the 1.6 in the proposal. In normal proposals, often you get one target or you get a C target. This makes your such a factor 1 to 3 or the 1 to 2, which everybody gets something. But here you have the full factor 1 to 6. Was there a second part of the question?
Yes, how successful are those?
From the Neil Brandt has published, this was the first one. He has published his catalogs, and I think this is taken enormously up. The other was Monique Arnaud with the clusters. I think there are also a lot of publications already out. The others we are still doing. We are only in the second. There was already a paper from this high redshift quasars. And they find a surprisingly 2.4 power law index in the mean, completely unexpected, which indicates that there is much more evolution with this high redshift than we maybe were expecting so far.
Okay, let's thank Norbert again.